Hi, everyone. So infinite geometric series, this is crucial in Calculus 2. Now, in general, geometric or not, an infinite series converges, by definition, if it has a sum. And you have a sum if the partial sums approach a real number. And I'm going to explain this in a moment. It's when the partial sums approach a number. Using this limit notation, the partial sums, S sub n, in the long run, as n approaches infinity, if you consider the sum of the first 100 terms, first 1,000 terms, first million terms, okay, if these cumulative sums approach a number, S, okay, then that number S is the sum of the series, and therefore the series converges. If not, the series diverges. Okay, if there is no limit, right? If the partial sums don't approach a number, there is no sum, and the series diverges. Every series either converges or diverges. Every infinite series either converges or diverges. Converges means has a sum, diverges means no sum. Consider the geometric series that goes like this. Okay, so the partial sums look like this. And in fact, I have some good pictures for this. Oh, let me try to get these here. Where are the good pictures? There we go. Okay, I have a bunch of good pictures here. This one over here. Okay. 1/2 of the pi plus a quarter plus an eighth plus a 16th plus yeah. This isn't my work, by the way. All right. Well, it looks like we're approaching, as we add on more and more terms, the sum, the partial sums are like the total areas we're picking up cumulatively. 1/2 plus a quarter is 3/4, plus 1/8, you get 7/8, plus 1/16, you get 15/16. There's a pattern there. It looks like we're approaching 1, the whole pi, right? Even think in terms of squares and rectangles, right? The area of this rectangle is 1/2, plus the area of this square, I guess, is 1/4, plus the area here is 1/8, plus da 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 da. Okay, we're approaching filling in the whole square. Now at no finite time, at no finite value of n, is it true that we have a partial sum of 1, but the partial sums are approaching 1, right? They're approaching 1. Okay, and later on we'll prove it using a formula. Okay, this series has a sum, it is 1. So if you plug these into your calculator and you add these all up, as you add in more terms, then the partial sums will be approaching 1. Okay, now, I guess I'll go back here. What is the common ratio here? The initial term was 1/2, but what's the common ratio? What do you multiply this by to get that? Actually, that is also a half. 1/2 times 1/2 is 1/4, 1/4 times 1/2 is 1/8, and so forth. So in this case, notice here, I forgot to make my point. R equals 1/2, and in this case, this geometric series converges because the value for R is crucial. By the way, let's assume a sub 1 is not 0. Okay, the value of R is absolutely crucial. This alone will tell you whether the geometric series converges or diverges. Assuming this is not 0, it doesn't even matter what this is. As long as this is any non-zero real number, right, then R is enough to tell you whether the whole series will converge or diverge. I mean, a sub 1 could have been 10 billion, right? If R is 1/2, you're going to get a sum. It'll be a huge sum, but there will be a sum. Okay. Now, the geometric series. We saw this before. We saw the sequence 2, 6, 18, 54. Let's consider the corresponding infinite geometric series. This has no sum. Look at the partial sums. 2, 8, 26, 80. I mean, these partial sums are approaching infinity. That means this has no sum. By definition, in order to have a sum, it would have to be finite, not infinite. Infinity does not count as a sum. All right, does not count. So this series does what? This geometric series diverges. It does not converge, therefore it diverges. And what's the key here? What was the common ratio again? R was 3. The multiplier to get from each term to the next term. Now, again, this series converged because R was 1/2. It was pretty close to 0, hint, hint. Here, R was not close to 0. It was 3. This series diverged, hint, hint. How about this here? Okay. The geometric series, this is a geometric series. 1 minus 1 plus 1 minus 1, and so forth. It's an alternating series. What are the partial sums? 1, 0, 1, 0. This reminds me of Bender's dream from Futurama. He was a robot. 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, like binary, right? See, here's the thing. These partial sums, even though they're not blowing up towards infinity, they're not approaching a single number. They're alternating between 1 and 0. So this is not approaching a single number. So this series diverges, all right? But in a different way. This series diverges more by oscillation. Okay, we might say that this geometric series diverges to infinity because the partial sums approach infinity. Okay, over here, this series diverges by oscillation because these partial sums just kind of wobble between the same two numbers, right? But these don't approach a single number, and you can't say 1/2. Although some software programs try to pull that. They try to say these approach a half. I don't quite buy that. All right, this has no limit, right? S sub n does not approach a real number as n approaches infinity. This series diverges by oscillation. And what was the value for r? Hey, what do you multiply by to get each new term? You multiply by r equals -1. All right. So for -1, you get kind of this weird behavior here. Divergence. So, and by the way, what happens if r equals +1? I don't know if I have an example like that, but what if we had 7 plus 7 plus 7 plus 7 plus 7 plus 7, and so forth? Here, the common ratio is 1, right? But wait, is this going to have, are the partial sums going to approach a finite number? See, 7, 14, 21. The multiples of 7 are not going to approach a number. You're going to diverge to infinity once again. So once again, this series diverges to infinity. And what was the common ratio? It was 1. All right. So notice that for r equals 1 and r equals -1, we diverge, right? But it's kind of a close call in these cases. If you're closer than 1 to 0, right? If you're at like 1/2 or -1/2, you converge. If you're more than 1 away from 0, you diverge. Bottom line, an a geometric series converges if and only if r is strictly between -1 and 1. That is, the absolute value of r is less than 1. And by the way, this was equivalent to the notion that the terms of the corresponding geometric sequence, the actual terms in the sequence, approach 0. Because this was also the same condition, right? R is strictly between -1 and 1. It was the same equivalent condition. So if r equals 1/2, converges. It's close enough to 0. If r equals 3, diverges. It's too far away from 0. If r is -1, you diverge. If r is 1, you diverge. Those are the borderline cases, but you do diverge at the borderline cases. These are strict inequalities. Now, this is called the harmonic series, the sum of the reciprocals of the positive integers, 1 plus 1/2 plus 1/3 plus 1/4. It's one of the most natural series that has the property that the terms approach zero, but this is not geometric. It's harmonic. It's called the harmonic series, but it's not geometric. So the rules I just told you about don't apply regarding common ratios. This has no common ratio, not geometric, no common ratio, all right? But the terms do approach zero. Now here's the thing. This is the easiest series whose terms approach zero. The terms of the series approach zero, and yet the series diverges. The series diverges. The terms of the series approach zero, yet the series diverges. It's not enough for the terms to approach zero, okay? When does an infinite series have a sum? We have clean rules for geometric series, but otherwise, calculus 2, you have like 11 tests for convergence or divergence, and they often don't tell you what the sum even is, if there is a sum. Okay, it's a challenge just to know, does it converge or diverge, right? Okay, so this is the easiest series where the terms approach zero and yet diverges. If you have a fishbowl in outer space where there's still gravity, huh? Okay, okay, you can pour in 1 gallon of water. The next day, what is a day? Well, anyway, an Earth day. The next Earth day, we pour in a half gallon of water. Then the next day, a third of a gallon of water. Regardless of how big that fishbowl is, the capacity could be 1 trillion gallons of water. Someday, could be a long time from now, the bowl is going to overflow. This diverges to infinity, but slowly. And why did we not care about infinite arithmetic sequences or series? I should have said series here. I'm sorry. No infinite arithmetic series has a sum. Okay, none of these guys will have a sum, right? There's no way that the partials will. For example, here this will diverge to infinity. There's no way the partials will settle down. If the geometric series has a sum, here's the formula. S equals the initial term over 1 minus r. It's beautiful. And it works if the series converges, because by definition, that's the only time you have a real sum. I mean, if r equals 1, that's messed up anyway. Cool example. Before, if I told you to write 1/3 as a decimal, what would you say? Okay, it's 0.3, right? Or in other words, 0.3 bar, which indicates repetition. That's a repeating bar or vinculum. That's in grade school. Now, in calculus, you often do the inverse problem, like we did with partial fractions, right? The inverse problem. I give you a repeating decimal. You find the corresponding nice fraction, integer over integer. So this is a property of rational numbers, right? They can be written in either form. Well, this is a number that can be represented as the sum of an infinite geometric series. This is 0.81818181 da 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 da. You can think of it as what? 0.81 plus 0.0081. Line these up. Plus 0.000081. These do line up. These do line up. 0.81 plus 0.0081 plus 0.00081 and so forth. I guarantee you this geometric series has a sum, and the sum is this number. This series has a property that the initial term is 0.81. Why is it a geometric series, and what's the common ratio? What do you do to get from here to here? You move the decimal point 2 places to the left. If you take a decimal number and you take the decimal point 2 places to the left, what are you doing? You're dividing by 100, which means you're multiplying by what number? You're multiplying by 1/100th or 0.01. And that is R. R is a penny, is 0.01. Which means, by the way, hey, that's close to 0. That means the series is going to converge. Okay, that R is certainly close to 0. All right, plug it into our handy dandy formula. S equals initial term 0.81 over 1 minus the penny. $1 minus a penny is 99 cents. Multiply top and bottom by 100 to clear the decimal points. 81 over 99. Divide top and bottom by 9. 9/11ths. Folks, get your calculators. 9 divided by 11. What do you see? You might get a 2 in there as a rounding thing, but there you go. The inverse problem. Pretty cool, huh? Summation notation, get practice on the homework, but the idea with summation notation is if you want to indicate a geometric series more generally, more abstractly, find the general nth term, or here the general kth term. We have that formula, the formula for the general kth term of a geometric, and stick on this operator, right? So these represent terms in the geometric sequence. Stick on this operator to get the series. Summation k equals 1 to infinity. In principle, you're taking all these terms and indicating the sum, adding them all up. And here we do have a sum. It's 9/11ths. Sometimes in calculus, you want to shift the index so that you start with 0 as the lower limit. And this cleans that up to an I. If you make the substitution, you make it look a little nicer. But I won't push you too hard on that in our class. But you will get used to that later. The idea of doing substitutions to manipulate the index, to make things look nicer. All right. Important stuff in calculus. It gets even cooler later. Next time.